So welcome to 8.1.1 oscillatory motion. And what we're going to be doing today is looking at some examples of oscillations. We're going to define a specific type of oscillatory motion, which is called simple harmonic motion. And you're hopefully going to be able to draw motion graphs for oscillations in simple harmonic motion. By motion graphs, I mean going back to topic 2 and looking at displacement, velocity and acceleration. So how do we define an oscillation? As you can see in this hummingbird, an oscillation is a repetitive variation, typically in time. In fact, in physics, we are going to be looking very, very closely at oscillations that vary in time and that tend to vary about a central value. So we can think about these wings as being oscillations about a central point in the center, with the wings moving backwards and forwards as time goes. And there are loads of different types of oscillations in nature. List: tides on the ocean, the movement of your legs as you walk, a heart beating, clock mechanism, atoms vibrating, machinery and engines, guitar strings. And I'll put an example of that on Google Classroom for you to watch. Your eardrums, electronic circuits, waves of various kinds. So these are all examples of oscillations. So your first task would be to find some examples, photos, lists, anything of an object vibrating in an oscillatory way. Maybe you could film something that's going on in your house, out the window, or you can find something online and link it on here. So find some more oscillations and stick them on here, please. Well, as stated, simple harmonic motion is a really specific type of oscillation. Isochronous is a very important word to consider when defining simple harmonic motion, because isochronous defines events that occupy equal amounts of time. Perfectly isochronous oscillations may not be possible in reality, but many real oscillators, like a swinging pendulum, for example, are almost isochronous. So an isochronous oscillation is one which is continuously oscillating in the same amount of time. Now, oscillations like these are called simple harmonic motions. So this is a pendulum, as you can see here, and what you're seeing is that it takes the same amount of time for a full swing, right? So this is something that is isochronous. And that's the beginning of a definition for the term simple harmonic motion. And another example of something that moves in simple harmonic motion is a spring oscillating in this way. Here you can see that the oscillation is about a midpoint, somewhere along here. Oops, hang on, if we have a look. Around here would be your equilibrium point. And you can see how the spring is moving up and below that midpoint continuously in the same amount of time. So that gives you your simple harmonic motion curve. Now let's have a look at how we represent that motion with something you might find familiar from your maths work. You can represent simple harmonic motion as a sine or cosine curve. We have a regular change, plus and minus, within the same period. Now this is a representation using time on your x-axis and displacement on your y-axis. And this is pretty much how we represent simple harmonic motion. There are some very important points on this graph. I'll switch here to a pendulum to show you the same thing. But on one of these graphs, you have a distance or a displacement which is maximum, right, which we refer to as an amplitude. That gives you an idea of how far away from that equilibrium point your oscillating object gets. So here on this displacement time graph, your amplitude is from the equilibrium point to the highest tip, or, and this should be exactly the same in magnitude, from the center to the bottom. Both of these heights give you amplitude. Now that's a very important distance on the displacement scale. But now on the x-axis, on the time axis, there's a very important piece of information that you can get, which is the period. Now, as we've already stated, what's important about this oscillatory motion is that the time is always constant. So the time it takes for this to move once is always the same. Doesn't matter if you do it once, twice, 3 times. That time for one oscillation is always the same, and it has a special name because it's that important. It's called the period of oscillation, and you can literally just read it off your your x-axis. Okay, so you just find, okay, where do we begin? We begin here. How long does it take the graph to get to exactly the same point? And that would be your period. Now, frequency is a way of defining the oscillations. It's the number of waves or oscillations, it's the number of swings, in this case in a pendulum, or vibrations in a spring, but it would be the number of oscillations per second per unit time. And the easiest way to calculate that would be to just take the period and do 1 over the period, and that would give you the frequency, the number of cycles or oscillations per second. Now this has units of s to the -1, that should have a -1 in there, I'll put it in, hang on, s to the -1, or hertz. Both of these are valid units for frequency. Okay, so you can measure your period by just finding how long it takes for a complete cycle, and then you can work out the frequency as 1 over period. Just a quick note, a complete cycle is for an entire oscillation to go back to its original position. So it does include above and below the equilibrium position. So if you're starting here, for example, a complete cycle, and I want you to shout out when you think you've seen a complete cycle, would be not there, but here, because you need a cycle to go all the way down and all the way up and then back to where you started. That is a complete cycle. What I'd like you to do now is to go to the assignment and to do these questions and apply what you've just learnt, and then come back to the presentation and learn some more. Now, simple harmonic motion graphs are just like any other motion graph in that they can represent not just the displacement, but also the velocity and the acceleration. So we're going to have a look at that first. If we have a look at a displacement time graph for simple harmonic motion, or your sine or cosine curve, whichever one's relevant, you can see that you have areas which have differing velocity. How do we know that? Because you guys have learned that the slope of a displacement time graph is equal to the velocity, and the slope is continuously changing. Now, with applying what you learned in topic 2, you should be able to sketch out a graph of velocity time for an object moving in simple harmonic motion simply by looking at the slopes. The first slope to look at, of course, is the easiest. You have a look at where the velocity is 0. Where on this graph is the slope equal to 0? I want you to stop the video and have a think and see if you can point out where you would have 0 velocity. Right, you're back. Good. So you've probably spotted that you have 0 velocity there because the slope is 0, and you have 0 velocity there, and there, and there, and there. So that's a really good start. That's where our velocity is going to be equal to 0. Now we're going to look at the slope directions, where the slope is a maximum and whether it's a maximum in the positive or the negative direction. Now you can see that here we have a maximum. Is it positive or is it negative? Right? I hope you said positive. So this means that the graph is greatest here in the positive direction, and also here, and also here. And where can you see that it's a maximum in the negative? I hope you said here. Good, because it's at a maximum, but this time it's negative. Well, if we have a look at our velocity time graphs now, you can see effectively we have 0 velocity here, here, and here, as we said before. And here we have maximum slopes. And here we have maximum slopes in the negative. I'd just like to point out that on Cognity, this is the Cognity page, there's a really nifty little program that lets you actually play around with the gradients and draw the motion graph. So I definitely recommend that when you do the reading, you have a good play with that. Anyway, back to our graph drawing. The next thing we can do, now that we have a velocity time graph and we understand why it looks the way it does, we can actually think about acceleration. How do we work out acceleration from a velocity time graph? Well, it's the slope of a velocity time graph, right? So if we look at the slopes for this graph, we can easily now draw a graph of acceleration over time in exactly the same way. We just need to find where is the value of acceleration equal to 0, because the slope is equal to the acceleration. So here we have 0. Here it's 0 again, here it's 0 again, and 0 again. So these are all points where you're going to have 0 acceleration. And then if we look at our slopes, we can see here's our first maximum, but it's minus. So it's going to be a maximum minus. And here we have a maximum positive, maximum minus, maximum positive. And there we can see our graph, right, which demonstrates what we were saying. Here's our 0, 0, 0, and 0. And what we have are maximum and minimum gradients. This is a minimum, which gives us our maximum minimum displacement here. And so there we have our acceleration time graph. Now what's really interesting is now if we compare this acceleration time graph to this one, what we can see is that it's the same. It's reversed, right? So you can see that where this is a peak in the maximum, this is a peak in the minimum. So what you have is that displacement is proportional to minus acceleration. The graphs actually demonstrate this rule. Now that is the beginning of the actual defining rule for simple harmonic motion, but we're going to carry on with that in lesson 2.